Today we are going to talk about metal semiconductor junctions. In the previous lectures, we talked about p-n homojunction under forward bias. We derived the equations for excess holes in the n region and for excess electrons in the p region. We also analyzed the behavior of excess carriers under forward bias. We derived ideal forward bias IV characteristics and looked at the operation of a tunnel diode. In today's lecture, we will look at energy band diagram of a metal semiconductor junction. We will derive the IV characteristics for a Schottky Barrier Diode. We will discuss the differences between a p-n junction and Schottky Barrier Diode. And finally, close towards the end, we are going to study ohmic contacts. So basically, there are two kinds of ohmic contacts. One are called ideal non-rectifying barriers, and the second one are tunneling barrier. First, let me tell you the difference between rectifying and non-rectifying. So rectifying means, for example, a diode which are going to allow current just in one direction. Non-rectifying, on the other hand, would allow current to flow in both directions. The Schottky Barrier Diode. Before describing that, let's first have a look at the p-n junction diode once again. How do you form a p-n junction diode? A p-n junction diode is formed by placing together a p-type material with an n-type material. On the other hand, we form a metal semiconductor junction by placing together a metal with a semiconductor material. This semiconductor material could be p-type or it could be n-type. And this kind of diode is called Schottky Barrier Diode, in which we have a metal deposited on top of a semiconductor material. Here is the symbol of a Schottky diode or Schottky Barrier Diode. One of the key properties of Schottky diode as compared to a p-n junction diode is that its turn-on voltage is lower as compared to the p-n junction diode. For example, in our previous lecture, we talked about p-n junction diode and we calculated its built-in potential. Depending on the doping of the p and n-type layers, its built-in potential varies in the range of 0.5 to roughly 0.9. We can say it's roughly 0.7 volts for the p-n diode. But on the other hand, for a metal semiconductor junction, this built-in potential or the turn-on voltage is 0.2 to 0.3 volts. And it's an advantage for a metal semiconductor junction because we want our diodes to have low turn-on voltage and high reverse breakdown performance. And because of the low turn-on voltage, it's going to have a low power loss and it's going to have high switching speed as well as compared to a p-n junction diode. Consider the energy band diagram of a metal semiconductor before making the contact. So here is our vacuum level. On the left side we have our metal with its Fermi energy level. Now about metals, we know that the conduction band and the valence band for a metal overlap with each other. So essentially the Fermi level is going to lie at the conduction and the valence band. This metal could be any material depending on the requirements. Here is a list of materials: silver, aluminum, gold, chromium, molybdenum, up to tungsten. And then the energy required to move an electron from the Fermi level to the vacuum level is called the work function of the metal, represented by phi m. And here we have listed the work function for different kind of metals as well. For aluminum, for example, the work function of the metal is 4.3. This difference between the vacuum level and the Fermi level is called the work function, represented by phi m. Why do we have the E symbol over here? Because phi m is in volts and everything else over here, the energy levels, these are energy levels. So we multiply charge with the potential so that we can also represent this value in terms of electron volts or energy. Similarly, for gold, the work function is 5.1 volts. Alright, we talked about the metal side. How about the semiconductor side? Assume that we have an n-type semiconductor material, and for the n-type semiconductor material, the Fermi energy level is going to be close to the conduction band. And similar to the metal, the semiconductor material will also have its own semiconductor work function represented by phi s, which is the energy required for an electron to move from the Fermi level of the semiconductor to the vacuum level. What is a vacuum level? Vacuum level is free space. It means to move carriers, or in case of n-type semiconductor material, to move electrons out of the semiconductor material into the free space, and that is going to be the work function of the semiconductor material. We also need to understand another terminology. It's called chi, or the electron affinity. Electron affinity is the energy difference between the vacuum energy level and the conduction band energy, or it's the energy required to move an electron from the conduction band to the vacuum level. Alright. The chi, or electron affinity, for different kind of materials is also fixed, just like the metal work function. For silicon, chi, or electron affinity, is 4.01. Now how about the semiconductor work function? Is it, so I'm asking you a question. Is the work function of the semiconductor going to be a fixed value as well, or is there any way for us to change it? Okay, how about the Fermi level of a semiconductor? Can we change the Fermi level of a semiconductor? We have that capability, right? We can do that by just doping. If we dope it p-type, the Fermi level is going to get closer to the valence band. And if we dope it n-type, it's going to be close to the conduction band. And depending on the doping, if you dope it higher, it's going to be closer and closer to the conduction band. Alright, so this work function for semiconductor is going to depend on if the material is n-type or if it is p-type, and also it's going to depend on the doping of the semiconductor material as well. Now in this case, in order to make a Schottky contact to an n-type semiconductor material, one of the primary conditions is that the metal work function should be higher as compared to the semiconductor work function. As you can see over here, here is your metal work function, and this is higher as compared to the semiconductor work function over here. Alright. Now what happens if we bring together the metal and the semiconductor? Now as we know that under thermal equilibrium, which means under no applied bias, the Fermi energy level should be constant. This is our EF. It should be constant as compared to the previous figure over here, where the Fermi level of the semiconductor is higher as compared to the Fermi level of the metal. But in case if we bring them together under thermal equilibrium, we should have a constant Fermi energy level, which means we have to bring down this level over here. And by bringing it down, there we also observe band bending on the semiconductor side, which means that electrons have flown from the semiconductor side to the metal side, resulting in a depletion region, leaving behind positive ions on the inside of the semiconductor material. And when these carriers flow to the metal side, they are going to introduce negative charges on the metal side as well. So essentially, for the metal semiconductor junction, we have separation of positive and negative charges, resulting in a depletion region. And most of this depletion region is going to be accommodated inside the semiconductor material, not inside the metal. As we discussed in the previous lectures, that the depletion width is inversely proportional to the doping concentration. Inside the semiconductor, this is lightly doped material. And over here we have metal. We have plenty of carriers inside the metal. So because this is lightly doped material, most of the depletion region or the band bending is going to be accommodated inside the semiconductor material. Here is your depletion region or the depletion width, which is going to be equal to Xn, or the width of the depletion region on the semiconductor side. Also, as we discussed for the PN junction diode, there is going to be a built-in potential for the metal semiconductor junction as well. This built-in potential is the barrier for electrons to flow from the semiconductor to the metal side. So VBI is built-in potential for electrons to flow from the semiconductor to the metal side. On the other hand, we also see another barrier. It's called phi B naught, or the Schottky barrier. This Schottky barrier is the barrier for carriers, or it's a metal, so for electrons to move from the metal side to the semiconductor side. So Schottky barrier for electrons to flow from the metal side to the semiconductor side. Right, phi B naught is Schottky barrier. Schottky barrier, how do we calculate Schottky barrier? Schottky barrier is going to be equal to the metal work function minus the semiconductor electron affinity. Look at the figure in slide number 5 over here. Here is your metal work function, and here is the electron affinity of the semiconductor. So phi m minus electron affinity is going to give you the Schottky barrier height. Alright, here is your Schottky barrier height equal to metal work function minus electron affinity. The built-in potential, on the other hand, this value over here is going to be equal to this Schottky barrier minus this, the difference between the conduction band energy level and the Fermi energy level. Or you can also represent EC minus EF with phi n. So VBI is equal to phi B naught, the Schottky barrier height, minus the difference between EC and EF, and you can also represent it with E phi n, or in terms of potential just with phi n. And these two equations are crucial, especially for your Schottky diode calculations. Now, what happens under forward bias? In the previous slides, we looked at energy band diagram of a metal semiconductor junction under thermal equilibrium. What happens under forward bias? Let us go back to this slide over here. Forward bias means this is an N-type semiconductor. So forward bias means to apply a positive voltage to the metal side and to apply a negative voltage to the N-type semiconductor. Applying a negative voltage to the N-type semiconductor means to drag these energy levels up. So if you apply a positive voltage to the semiconductor, it's going to drag down the energy levels of the semiconductor, all the EC, EF, and EV energy levels. But if you apply a negative voltage to the semiconductor, it's going to drag up the energy levels, all the levels EC, EF, and EV. So apply a negative voltage over here. It means the diode, now the Schottky diode is forward biased. So now the Fermi level on the semiconductor is going to be slightly above the Fermi level on the metal side. So here is your energy band diagram under forward bias. Apply positive potential to the metal, negative potential to the semiconductor. The semiconductor energy levels would be dragged up, which means the Fermi level on the semiconductor is going to be slightly higher as compared to the Fermi level on the metal side now. But what happens to the barrier? Now, this built-in potential which originally was VBI under thermal equilibrium for electrons to move from the semiconductor to the metal, it's reduced now. Compare it with the thermal equilibrium barrier height for electrons to move from the semiconductor to the metal. Now under forward bias, this barrier has reduced, and now it's equal to VBI minus VA. So under forward bias, it's going to be easier for electrons to move from the semiconductor to the metal. Now look at the Schottky barrier height. Do you see any changes in the Schottky barrier height as well? No, the Schottky barrier height remains the same. So the barrier for electrons to move, Schottky barrier height is phi b naught. So the energy required for the current to flow from the metal, the barrier height, is still going to be the same, but now it's easier for carriers to flow from the semiconductor to the metal. And this current mechanism is due to, as this is due to the flow of electrons. This is an N-type semiconductor material. Electrons are majority carriers in N-type semiconductor. So the current mechanism in Schottky barrier diodes is due to the flow of majority carriers. In the PN junction diodes, we discussed that the current flow is due to minority carriers diffusion. But in case of Schottky barrier diodes, the current flow is going to be due to the majority carriers, or for an N-type semiconductor, it's due to electrons. What happens under reverse bias? Reverse bias means apply a positive voltage to the N-type semiconductor material. If you apply a positive voltage to the N-type semiconductor material, now the Fermi energy levels you drag down. If you apply positive voltage to the semiconductor side, you drag down all the energy levels on this side of the junction, which means that the Fermi energy level of the semiconductor is now much lower as compared to the Fermi energy level on the metal side. And the barrier height for electrons to flow from the semiconductor to the metal has drastically increased now. Now it's equal to EVBI plus VR. Also, as you can notice that now the depletion width, which is represented by the band bending, or over here you can see it represented by this depletion region, this width has now increased as well. So under forward bias, the depletion width is going to be reduced. This depletion width is going to be reduced, and the barrier for electrons to flow from the semiconductor to the metal would also be reduced. But under reverse bias, this barrier height is increased for electrons to flow from the semiconductor to the metal, and the depletion width represented by the band bending, or over here by the charges, also increases. How do we calculate electric field for metal semiconductor junction? It's similar to the PN junction diode. You can calculate electric field by using Poisson's equation. The derivative of electric field with respect to x is equal to charge density, and then you integrate the charge density, and after solutions and a couple of simplification steps, you get a relationship for the electric field. Now at this metal semiconductor junction, as we discussed for a PN junction diode, the maximum electric field for a metal semiconductor junction would also be at the origin along the metallurgical junction. So put x is equal to 0 in this equation, you get a formula for calculating the maximum electric field in this metallurgical inside this depletion region. So our Emax is equal to END Xn divided by permittivity. Nd is the doping of the semiconductor, Xn is the depletion width on the N side, or basically on the semiconductor side, because most of the depletion width would be accommodated on the semiconductor side. And then here is a formula. We can perform the derivations, and here is a formula for calculating the depletion width of the metal semiconductor junction, which is equal to 2 times permittivity of the material times the built-in potential plus reverse bias applied voltage. If this is reverse bias, you add it to the built-in potential. If this is forward bias, you subtract it from the built-in potential, divided by E is the charge of electron and Nd is the doping of the semiconductor material. Now consider this example. In this example, we know that we have a metal semiconductor junction, an N-type material, and we have a metal. And we are required to determine the barrier height, the built-in potential barrier. This is our barrier height, the built-in potential, and the maximum electric field in the metal semiconductor diode for zero applied bias. Zero applied bias means under thermal equilibrium. So, and then they are asking us to consider a tungsten metal and an N-type silicon doped as Nd is equal to 10 to the power of 16 per centimeter cube at T is equal to 300 Kelvin, which is basically room temperature. Now, if we look back into the table in the previous slides, the work function for tungsten is 4.55. Alright, so the work function for tungsten is 4.55 volts. Now, we can easily calculate the built-in this Schottky barrier, the potential barrier over here on the metal side, and it's equal to the metal work function minus electron affinity of the semiconductor. And also in that previous slide, we know that electron affinity for silicon is 4.01 volts. In the metal work function, we have used a tungsten metal, so its work function is 4.55. So this barrier height, or the Schottky barrier, is going to be 0.54 volts. How about the built-in potential on this side? The built-in potential is the difference between this barrier height and phi n, which is EC minus EF. Alright, we know phi b naught. We have calculated phi b naught, the Schottky barrier height, but we don't know phi n. So here is the formula for calculating phi n, and we previously discussed it. It's kT by Q, which is thermal voltage, 26 millielectron volt approximately, times natural log of Nc. Nc is the density of states in the conduction band. Its value is a given value, a fixed value for a particular material. 2.8 10 to the power of 19 for silicon per centimeter cube. And our doping concentration is 10 to the power of 16 per centimeter cube. So phi n, this difference between EC minus EF, comes out to be 0.206 volts. And then you can easily calculate the built-in potential by subtracting phi n from the Schottky barrier height, which comes out to be 0.334 volts. And you can compare it with the PN junction diodes. Generally for PN junction diodes, the built-in potential is roughly 0.7 volts. So for metal semiconductor junctions, the built-in potential is much lower as compared to the PN junction diodes. And also, what else is required over here? The maximum electric field. We are also required to calculate the maximum electric field. Here is the relationship for maximum electric field. We know the doping, we know the charge on electron, we know permittivity of the silicon, but we have to calculate Xn, which is width of depletion region. And here is a simple formula for calculating Xn. It's under thermal equilibrium, so we don't add or subtract applied voltage. VBI is the built-in potential. We can easily calculate Xn, which comes out to be 0.208 10 to the power of minus 4 centimeter. and then using this relationship, our electric field comes out to be 3.21 into 10 to the power 4 volt per centimeter. Junction capacitance, which is given in farad per centimeter square. So as we previously discussed in case of a PN junction diode, that whenever we have separation of positive and negative charges, there is going to be junction capacitance. Separation of charges is going to result in capacitance. How do we calculate the junction capacitance? And this is given in farad per centimeter square. So if you want to calculate the capacitance, just multiply the junction capacitance with the cross-sectional area of the diode, and you would be able to achieve the capacitance. How do you calculate the capacitance? We know that charge is equal to capacitance times voltage, which means capacitance is going to be equal to charge, which is E and D dxn divided by dVr. And from the previous slides, if you take the derivative of xn with respect to reverse bias voltage, you get a simpler relationship for calculating the junction capacitance for a metal semiconductor junction, which is proportional to the doping concentration, inversely proportional to the built-in potential, and the reverse bias applied voltage. And it's going to be in farad per centimeter square. Now, previously we also discussed that we can also experimentally determine the junction capacitance for a PN junction diode. So similar to that, we can also perform the same analysis on the metal semiconductor junction, and the goal over here is not to calculate the junction capacitance. The goal is to calculate the doping concentration. So basically you perform CV measurements, you apply reverse bias voltages, and you have a capacitance meter, and using that you measure the capacitance and then take 1 over C square of that, and then plot the results. For example, this is a plot for tungsten metal deposited on top of gallium arsenide material, and here is another. Let's consider the example of tungsten applied on silicon instead. So you increase the voltages and you just measure the capacitances and then calculate 1 over C dash square and then just plot the values, and you would be able to achieve a straight line. Over here, 1 over C dash square is your dependent variable, VBI plus VR is your independent variable, and 2 divided by charge on electrons times permittivity times doping concentration is the slope of this line. So if you just simply calculate the slope, from the slope you can calculate and ND as well. For example, over here, assume the range of a reverse bias voltage of 1 to 3 volts. So for a value of 1 over C dash square is 6 10 to the power of 13. For a value of 3, it's approximately 12. Take the difference between the two, 12 minus 6, it becomes 6 10 to the power of 13 divided by 3 minus 1, 2. So from over here, this becomes your slope, and that is going to be equal to 2 divided by EES and D. You know charge on electron, you know permittivity of the material. You can easily experimentally calculate the doping concentration of the semiconductor material from just measuring the slope of this line. So this is an experimental way. If you don't know the doping concentration of your Schottky barrier diode, you can experimentally calculate the doping concentration by performing CV measurements or capacitance voltage measurements. Right, an example based on this as well. To calculate semiconductor doping concentration and Schottky barrier height for silicon diode, experimental capacitance data shown in figure 9.3. So as already discussed, just find the slope over here and then equate it to 2 divided by EES and D. So the slope came out to be approximately, I thought it was 6, but it came out to be 4.4 10 to the power of 13 per 10 to the power of 13. Now equate it to 2 divided by E, ES, and D, charge on electron, permittivity of silicon, and then this is your slope. Reorder the equation to calculate ND. ND comes out to be 2.7 10 to the power of 17 per centimeter cube. So we found ND, and now we are asked to calculate Schottky barrier height for this tungsten silicon Schottky diode as well. And our Schottky barrier height is, like, if you look at the energy band diagram, one way to calculate the Schottky barrier height is to subtract electron affinity from the metal work function. But another way is to, this Schottky barrier height is also equal to the built-in potential plus phi n, where phi n is the difference between conduction band energy and the Fermi energy level. So we use the second approach to calculate phi bn, or the Schottky barrier height. VBI, which we can calculate, or VBI is already given, alright, and VBI can also be determined from the intercept of this line. The intercept of this line is somewhere close to minus 0.4 volts. So we know our VBI, we don't know phi n, but we can easily calculate phi n from this relationship, where NC once again is a fixed value for semiconductor material, the density of states in the conduction band. For silicon, its value is going to be this one in the conduction band, but in V and the valence band, it's going to be a different value. ND is our doping concentration, which we experimentally determined from the CV measurements, and from over here you just add up the built-in potential and this potential phi n, the difference between EC and EF, you calculate the Schottky barrier height. This comes out to be 0.52. And the Schottky barrier height is also, you can say, it's the difference between electron affinity and the metal semiconductor. So that is another way to calculate Schottky barrier height. The Schottky diode IV characteristics. Excuse me. Now current in the Schottky diode is going to have two components. Excuse me. So if we apply a positive voltage to the metal semiconductor junction, as I already discussed, forward bias, under forward biasing, which means apply negative voltage to the n-type semiconductor. If you apply negative voltage to the n-type semiconductor, you drag up the energy levels on the inside. So in this case, the Fermi level of the semiconductor is going to be slightly above the Fermi level of the metal, and your applied voltage is accommodated over here, the difference between the semiconductor Fermi level and the metal Fermi level. Alright, the current across the Schottky diode is going to have two components. One component is the current that is flowing from the semiconductor to the metal, and it's going to, under forward biasing, it's going to have a really small barrier. And the second component is the current that is going to flow from the metal to the semiconductor. But over here we have a barrier we have a big barrier for electrons to flow from the metal to the semiconductor. So predominantly this part is going to dominate the total current. And I don't want to go into the derivations, but here is the relationship for current density in amperes per centimeter square for a Schottky barrier diode, which is equal to A star T square e to the power of minus. A star is called effective Richardson constant. T is the temperature. Phi Bn is Schottky barrier height. Kt is, once again, K is Boltzmann constant, and T is the temperature. N2 exponential of EVA divided by KT minus 1. And the effective Richardson constant can also be calculated using this relationship. H is the Planck's constant, K is Boltzmann's constant, Mn star is effective mass of electrons inside the semiconductor material, E is charge on electron. So this part you can say this is the reverse saturation current for the metal semiconductor junction. So you can replace it by JST, this part over here, in times e to the power of EVA divided by KT minus 1. Now, this equation looks familiar as if you compare it with the PN junction diode. In the PN junction diode, we said that J is equal to J is not the reverse saturation current. The way to calculate J is not for a PN junction diode is different, but it looks similar. So we have a reverse saturation part in the PN junction diode. Similar to that, we have a reverse saturation current part in the Schottky Barrier Diode as well, times e to the power of EVA divided by KT minus 1. This part is the same in both the equations, where VA is the applied voltage. Excuse me. Right. Here is an example of calculating the effective Richardson constant. So in this example, we are required to determine the effective Richardson constant from the current voltage characteristics. Consider a tungsten silicon diode in this figure. This is our tungsten silicon diode current versus voltage characteristic plotted on a semi-log scale, and assume a barrier height of 0.67 volts. The barrier height is given. The reverse saturation current is not given, but we can calculate JST from this plot. JST is basically the current at 0 volts under no applied bias. So JST is approximately 6 into 10 to the power of minus 5 amps per centimeter square. We have this equation for JST from the previous slide, the reverse saturation current. Effective Richardson constant times temperature. Over here we have the Schottky barrier height, Boltzmann constant, and temperature. Reorder the equation, and from this equation we can easily calculate the effective Richardson constant. It comes out to be 114 amps per Kelvin square or centimeter square. One thing to notice is that the effective Richardson constant is a strong function of the Schottky barrier height. With increase in barrier height, the effective Richardson constant is going to increase exponentially. Comparison of a PN versus Schottky diode. Now, as I already discussed, that a Schottky diode has a excuse me, has a lower turn-on voltage as compared to a PN junction diode. For a PN junction diode, the turn-on voltage is roughly 0.6, 0.7 volts. For a Schottky diode, we calculated it in one of the examples. It came out to be 0.33 or something like that volts. So Schottky diode has a smaller turn-on voltage as compared to the PN junction diode, and we can also observe that on this full scale of forward and reverse bias, where the turn-on voltage is lower for a Schottky diode as compared to the PN junction diode. And and what do we want? We actually want lower turn-on voltage for diodes. So Schottky diode has a better IV characteristic or better performance as compared to the PN junction diode under forward bias conditions, because low turn-on voltage also means low power loss, and it also means faster switching. Now let us look at the reverse voltage characteristics. Under reverse bias, the PN junction diode has higher breakdown voltage as compared to the Schottky barrier diode. Now, I told you that under forward bias, we want to have a low turn-on voltage for diodes, and Schottky diode behaves better as compared to the PN junction diode. But in case of reverse biasing, it is desired to have high breakdown performance. So PN junction diode performs better in reverse bias, but a Schottky diode performs better under forward bias conditions. So far we talked about rectifying contacts. A metal semiconductor junction with a rectifying contact, which means we talked about diode behavior. Rectifying contacts are going to allow current to flow just in one direction. Now we want to talk about non-rectifying contacts as well. Non-rectifying contacts would allow current to flow in both directions, from the semiconductor to the metal and from the metal to the semiconductor. Let me go back to the rectifying contacts, to this plot over here, or let us consider it under forward biasing somewhere. Slide number 15. Under forward biasing, there is a small barrier for electrons to flow into the metal, but there is a big barrier for current to flow from the metal to the semiconductor. So we are allowing flow of current just in one direction. In this contact, that's why this is called a rectifying contact. On the other hand, non-rectifying contacts would allow current to flow from the semiconductor to metal, but also it's going to allow current to flow from the metal to the semiconductor as well, which means conduction of current or conduction of carriers in both directions, and that is the key property of non-rectifying contacts. There are two types of non-rectifying contacts. One is ideal non-rectifying barrier, and the second one is tunneling barrier. Consider a metal semiconductor, a metal in a semiconductor, and then we place them together and form their junction. Now, previously, for a rectifying contact or for a Schottky contact, if this is your n-type semiconductor material, let us go back to the previous slide. What is the condition for metal work function versus the semiconductor work function for a rectifying contact? For a rectifying contact, the metal work function should be greater than the semiconductor work function for n-type semiconductor material. But on the other hand, for non-rectifying contact, it's the opposite. Now the metal work function should be lower as compared to the semiconductor work function, and you can see that over here. Here is your metal work function phi m, and here is your semiconductor work function running from EF to the vacuum level. And as you can see that the metal work function now is lower as compared to the semiconductor work function. So you should know if your phi m is greater than phi s for n-type semiconductor, that means you are going to have a rectifying contact, and that is going to show diode behavior. But if your metal work function is smaller as compared to your semiconductor, you will see a non-rectifying contact. It's going to be closer to ohmic contact, and it depends on the application. If you want to form a Schottky diode, if you want to see a diode behavior, you want your phi m to be greater than phi s. But if you already have a diode structure, a device structure, and if you just want to apply contacts to it so that you can extract current from it, then you want non-rectifying contacts, and in that case your phi m should be less than phi s for n-type semiconductor material. Now what happens if you bring together these the metal with the semiconductor? Under thermal equilibrium, the Fermi energy level should be constant, so which means this Fermi energy level is going to be slightly dragged up, as you can see over here, and that is going to introduce some sort of band bending as well. Now we still, so if you look at electrons, what is the barrier for electrons to flow from the semiconductor to the metal? There is no barrier for electrons to flow from the semiconductor to the metal. Electrons can easily just trot into the metal. How about current to flow from the metal to the semiconductor? There is a barrier, but as compared to the previous structures, to the rectifying contacts, it's a really small barrier. So under the application of a voltage, current, electrons should also be able to flow from the metal to the semiconductor as well. And this barrier over here is called phi bn, just like the previous case, the Schottky barrier. And it's going to be equal to, almost equal to phi n, or the difference of EC minus EF. If you apply a positive voltage to the metal, you drag down the metal Fermi energy level. So if you this is for applying positive voltage to the metal, negative to the semiconductor, and here is your energy band diagram. Electrons can easily flow from the metal, from the semiconductor to the metal, and also the reverse is also true. A small barrier, but still electrons can flow from the metal to the semiconductor as well. Now here, if you apply positive voltage to the semiconductor side and negative to the metal, we are going to drag down the semiconductor energy levels, and the electrons will now and that is going to be a slight reverse bias condition, but still electrons would be able to flow from the semiconductor to the metal, but there is going to be a small barrier for electrons. But then it's going to be easier for electrons to flow from the metal to the semiconductor side, and this barrier height is equal to phi n. The difference of phi n is the difference of EC minus EF. This is this barrier height over here. Right, I'm going to try to finish the lecture just in one go. We have like five or six slides left. All right. So in the previous slides, we considered N-type semiconductor. How about a P-type semiconductor? What are the conditions for non-rectifying barrier for a P-type for a P-type semiconductor? For metal to P-type semiconductor, we have a metal and we have a semiconductor, and the semiconductor now is P-type. How do we know that? The Fermi energy level for a P-type semiconductor is going to be close to the valence band. So if we want to form a non-rectifying contact to metal contact to the P-type semiconductor, the metal work function should be greater than the semiconductor work function. This is the primary condition for this case. And as you can see, the metal work function running from EF to vacuum for the metal is greater as compared to the semiconductor work function running from EF to the vacuum. And then you place together the semiconductor, which is P-type, and the metal, and now this Fermi energy level is slightly higher as compared to this, and under thermal equilibrium it should be constant, so you drag it down and all the other energy levels would also bend downwards. So now in this case, holes easily flow upwards. So it's really easy for holes to flow from the semiconductor to the metal, and for carriers to flow from the metal to the semiconductor, there is going to be a small barrier represented by phi BP, which is just the difference between EV and EF. So a small barrier, but still it's going to be easier for the current to flow in both directions for non-rectifying barriers. A tunneling barrier. We discussed the topic of tunneling in one of the previous lectures, and as I told you that tunneling actually happens under heavily doped conditions. What is a heavily doped condition? If the carrier concentrations are above roughly 510 to the power of 17 per centimeter cube, it's heavily doped material. If it is below 510 to the power of 17 per centimeter cube, it is lightly doped material. And then here is relationship for the depletion width, and it's inversely proportional to the doping concentration. If the doping concentration is high, the depletion width is going to be lower. Now, how does it work? Here we are given to calculate the depletion width for this doping 710 to the power of 18. It is much higher as compared to the threshold level 510 to the power of 17. So it means we have a heavily doped condition. Now we want to calculate the depletion width represented by this formula. The doping concentration is 710 to the power of 18. Calculate the depletion width, and it comes out to be 110 angstrom. It's just 11 nanometers as compared to the previous examples, it's a really thin depletion region. Now look at the energy band diagram. What kind of materials do we have over here? The Fermi level is close to the conduction band, so it's an N-type material, but it's lightly doped. And then on top of that, we deposit an N plus material, where the Fermi level is super close to the conduction band. So this is our layer which is heavily doped, and this is going to result in tunneling. And then we have our metal on this side. Now the depletion region, this region is really thin, approximately 11 nanometers. If it is super thin, carriers would get an opportunity to tunnel through this layer instead of crossing over the barrier from the metal to the semiconductor or from the semiconductor to the metal. And that's why tunneling barriers allow carriers to flow this way from the semiconductor to the metal through the barrier using tunneling, and also from the metal to the semiconductor via tunneling. Alright, I already discussed this, that if the doping increases, the depletion width is going to be reduced, and if it is reduced, we give a chance for the carriers to tunnel through this thin layer. And then tunneling occurs at heavy doping. Now here is the relationship for tunneling current density in amps per centimeter square. It's proportional to phi bn, and there we have a minus sign in the exponential, so that means if your Schottky barrier height is higher, your tunneling current would be lower because we have a minus sign in the exponential. And then it's also proportional to E naught naught, E00, and then E00 is proportional to ND. So if the doping concentration is higher, your tunneling current is going to be higher as well. So two conditions: if your barrier height is lower, it's going to result in a high tunneling current, and similarly if your doping concentration is higher, it's going to result in a high tunneling current. And then specific contact resistance. Alright, specific contact resistance is a figure of merit for contacts to devices. For example, if you have manufactured a p-n junction diode, you need to make contacts to the p-n junction diode. But if your contacts are Schottky, you don't know if the diode behavior is coming from the p-n junction, or if it is coming from the metal to the semiconductor contacts, or if it is a compound effect of the two. So you need to measure your specific contact resistance to determine where the diode behavior is coming from. And for making contact to devices, for example, to p-n diodes, to PIN diodes, to HEMTs, to lasers, to LEDs, you want to have low specific contact resistance, or you want ohmic contacts. You want to make ohmic contacts to these devices. So how do you calculate specific contact resistance? The inverse of the derivative of the current density with respect to voltage. For a rectifying contact, for a Schottky diode, here is your relationship for the current density. Alright, and from here, calculate using this relationship, you can calculate specific contact resistance, which is proportional to phi bn. So for a rectifying contact, for a Schottky contact, for Schottky diodes, your specific contact resistance is going to be higher for higher Schottky barrier height. The higher the Schottky barrier height, the higher the contact resistance is going to be. For tunneling, it's inversely proportional to the doping concentration. The higher the doping concentration, the lower the contact resistance. And we can look at it with the help of a plot as well. So just consider the first condition, and that is what happens to the what happens to this contact resistance if we increase the Schottky barrier height from 0.4 to 0.6 to 0.85. By increasing the Schottky barrier height, our contact resistance increases from 10 to the power minus 5 ohm centimeter square to 1 approximately to approximately 10 to the power 4 ohm centimeter square. Now let us consider the second condition. What happens if we vary the doping? And the doping is, we are increasing the doping on this scale from 10 to the power 17 to 10 to the power 20 per centimeter cube. So for each case, for each barrier height, now your specific contact resistance is decreasing. So if you want to form ohmic contacts, a good way to do it is to increase the carrier concentration of the semiconductor material. And I've actually grown devices, and I've fabricated devices, and I've measured specific contact resistance. There are actually procedures to measure specific contact resistance. In literature, for good devices, the specific contact resistance is somewhere in this range, 10 to the power of minus 3 to 10 to the power of minus 5 ohm centimeter square. Personally, I've achieved 10 to the power of minus 5 ohm centimeter square. Any contact resistance above these values is going to be too high. It's going to introduce a large voltage drop in your devices. That kind of concludes the lecture part of these slides, and then here is your homework number 3. Please solve problems from 9.1 to 9.7, 9.14, 9.15, and 9.25. So as compared to the previous assignments, I've reduced the number of problems for you to solve, right? You all should be happy for that, and thank me for that. Thank me later. All right, that concludes the lecture. Thank you so much for your kind attention. And the next week on Tuesday, we will coordinate about the time. We will please decide the time among yourself. But next week we will perform Silvaco TCAT simulation of a Schottky diode and it's going to be an in-person session at KIPE. So please collaborate with each other for that. Right? Take care. See you next time, inshallah.